Okay, good morning, everyone. I am very happy to see you all here. Thank you for coming. Thank you very much. And all right, I'm going to present briefly the status of the flagship beam lines, let's put it like that. However, there are many things going on, so feel free to contact the scientists. They are all over here, you know. So visit the beam line if you want and get in touch with them. So, well, as you know, second year of operation of the EVS, return to normal user life. That's why we are all here today. So we are really happy, and we hope that it will be like this in the coming years. So as you know, we are, I mean, in the experimental division, well, experimental hall, it's profiting quite a lot from the great new capabilities in terms of emittance, brilliance, and transverse coherence. So the beam lines are expanding their possibilities, multi-scale. Well, you have seen already some of the new highlights from yesterday from the tutorials. From probe, superior time resolutions, condition, we are going extreme, more extremes, better sensitivity, throughput, selectivity, and we are starting to apply machine learning algorithms to our data pipeline, data analysis as well. So in that context, let me just remind that in the first phase of the upgrade program, there were all 19 beam lines upgraded, I mean refurbished. And then in the second phase, in total 10 beam lines, I'm going to present the most important, well, the ones that they are right now at operational or almost by the end of their construction phase or in plan. So this is just the overview of the ongoing and planning major beam lines. You are going to see 3 talks from the beam line scientists for ID3, ID21, ID24. So I will not say anything about it because you will get it later. And let me start just reminding first the application of these new beam lines and then a brief update of their status. So BN18, well, this is Volta-Ferro for phase contrast tomography, multi-scale, applied to biomedical imaging. We have here quite a lot of users, industrial applications, geology, material science. The second beam line is ID 14, actually it's ID 18 that will be moved by the end of the year, the nuclear resonance scattering, to study electronic properties of magnetism at extreme conditions for magnetism, as I say, at megabars, geoscience, superconductivity, and so on. The third one that I decided to include is a new beam line for serial macromolecular crystallography, time result studies applied to drugs designs, to biofuels, to bioremediation, photobiology. Daniel is around as well. And finally, the flagship beam lines, which profit from the coherence of our new beams for X-ray dynamics and imaging, applied to mesoscale structure dynamics, pieces of, you know, crowded systems, glacier states, and so on. So let me just give you quickly, because it's 10 minutes, the update of the beam line. Just the high throughput large field, as I say, BN18, is operational since September 2022 with a small sample stage. I mean, the big one for 300 kilograms and 2.5 meters sample size is under test in Belgium right now. The lab is motion lab, and we expect the delivery of the sample stage by March 2023. So by June 2023, we hope that we can offer the new sample stage to the users. The ID14 beam line is progressing quite well. I mean, the beam line is, well, deal with the decay of nuclear levels, resonantly excited with a sharp pulse X-ray beam. Right now, the spectrography is in use in ID18. The nanoscope will be ready by June, so in ID18. By the time that we are talking now, let me see, here is the status of the construction in ID14. So it's progressing quite well. We are in the completion phase of the purchases. the installation of the granite and all the equipment in the optical hutches 1 and 2. And the beamline should be operational for the users in February 2024, March 2024. Well, SACHA is as well around. Then we have ID 929 for X-ray exterior crystallography. The beamline is operational. This is one of the most important flagship beamlines within the EBS array of set of beamlines. Here you have the first patterns from a protein crystal collected at 70 microsecond pulse with a quite high frame rate. The Jungfrau, I think that is well integrated with the Lima 2. And the beamline already is taking users experiments. The first users were in September 2022, and actually they use 4 different delivery systems in free experiments. So it's quite on track. And this is just the planning. As you see, they are in 2023, well, Marine Code will talk about 21, which is already in the final stage of the DCM double crystal monochromator commissioning. We expect that by 2024, we will have ID3 and ID18 already operational. And finally, by 2025, the coherence beamline plus ID26, which actually needs also a new DCM, apart from the recovery of the optical hutch. So we hope that in the coming year, we are going to keep the highlights, I mean, the scientific highlights, study material on the string conditions, ID27, ID15, where we have quite a lot of breakdowns results last year from ID11 as well, and many beamlines that they are now moving to high pressure, high temperature conditions. Quantum phenomena, ID32, ID20, green transition, this is transversal area. We know we have a battery hubs, and Drink will give you a talk later. Also, a lot of studies going on in catalysis, in additive manufacturing. And finally, as usual, learning from nature. I mean, we are scanning organs, we are scanning plants, we are scanning fossils, meteorites, and we keep going, and we hope that this will be the trend and even will enlarge our applications in the coming years. Finally, I just mentioned this high visibility result. I suppose that Marie will present it, so I will not do any spoil, but you have seen it on the news, the detection of lead compounds within the Rembrandt nights. And with this, thank you for your attention.
Thank you, Gemma. As you can see, a lot of things going on, and more things will be going on. Any questions? Okay, if not, then we move to the 3 reports from the beamlines, and we start with Karsten, that will tell you a little bit more of the status of the ID3 project.
Okay, there's still plenty of space here in the first row. Somebody wants to sit down. So this starts at the end, which is not really where I wanted to start. I'm going to present you the progress on ID3, which is the new hard X-ray microscope at ESRF. And we have actually built a hard X-ray microscope already on ID6, which has been in use operation for about a year, has been shut down now for this move in just before October, and is now being implemented on a completely new beamline with fully dedicated, fully optimized optics, and with twice the amount of beam time available. So I see a lot of potential users here. You're all welcome to submit your proposals, and I hope to see you on the beamline soon. Dark field microscopy is a technique that we've been developing since about 2013-14, so it's fairly new. And it's a combination of X-ray topography, so making images of diffracting crystals or crystalline elements in samples, but putting an X-ray objective in between the sample and the detector. That has several effects. One is that it magnifies the image, so we can reach a spatial resolution that's on the order of 100, 150 nanometers. But also the objective acts as a pinhole in the diffracted beam. So with that, we actually gain quite high resolution in the scatter beam directions, which is not the case for typical X-ray topography, where you have a detector in the near field and you basically have very little resolution in the scattered angle and then in the transverse direction. It's a full field method. It's non-destructive. And because it's non-destructive, it can be used in situ to follow processes as they go along. So it's conceptually very, very similar to electron microscopy, transmission electron microscopy. We have worse resolution, of course, but we have the huge advantage that we can work with much thicker samples, bulk-like samples that don't need to be specially treated. We can measure in transmission of millimeter-sized pieces of aluminum or other metals and biominerals and things like that. We have much better strain resolution because our angular acceptance of the lens is much better, and the X-ray incident beam is much higher collimated than the electron beam typically. And because it's hard X-rays, we can work in air, we can go through capillary sample environments and things like that. So key parameters, typically we work at X-ray energies between 15 and 20 keV. We can go up to 30 keV approximately. And we have a working distance between the sample and the X-ray optics of about 20, 30 centimeters. And that leaves a lot of space for sample environments. For example, for metallurgy, we've had load frames to actually pull and plastically deform the sample during the experiment. We have furnaces, we have cryogenic environments and things like that. And that allows us to do a lot of in situ experiments, which are not possible with electron microscopy. We're working now on multi-scale operation, meaning that we want to combine our very high resolution technique that looks at one Bragg reflection of one crystal grain within the sample, to put that grain into a context, look at the neighboring grains, know what the relation is between the orientations, and potentially in the future also be able to automatically switch from one grain to another and do studies of several adjacent grains or crystalline columns in shells, for example, and things like that. And we want to integrate that, especially with 3D XRD and diffraction contrast tomography. And we already can do 3D studies by focusing the beam onto a line and then doing section topography, illuminating one layer at a time of the sample, and then in software stacking these layers to create a 3D volume. And therefore, not only seeing projections, but really seeing 3D images. There's a second technique which we want to develop, which is called topotomography, where you rotate the crystal around the Bragg vector. And we have ordered a new diffractometer, which will allow that mode of operation. And we hope that that will be giving new insights and new contrast mechanisms that we can exploit. So what is the technique good for? This may look a bit familiar, the format. Our main field of application right now is metallurgy. We have a relatively large community of users that look at metals, plastic deformation of metals, recovery, meaning that when you have a deformed metal, you start to anneal it, and then defects start to move around, to disappear, the crystal quality becomes better, grains grow, recrystallization occurs. That is a very large percentage of our users right now. The second large group is functional materials, especially ferroelectrics, where we can see the ferroelectric domains, and we can see how these ferroelectric domains are modified by the application of an electric field, by heating or cooling. And we can not only see the arrangement of the domains, which you can sometimes see with polarized light microscopy, but we can also see the strain patterns and the strain distributions within these domains. We have had some first experiments with biominerals where we had problems with intensity. We hope that with the new beamline, we will have much more intensity, so we should be able to also look at more biominerals. And we've looked at ceramics. So just to give you an example from metallurgy, this is an experiment that was done by Leroy Dresselhaus in collaboration with John Ilgrim, who's somewhere hiding in the back there, didn't come to the front row. We had a single crystal of aluminum that was before the experiment already quite well annealed. So we have a quite small number of dislocations, lattice faults, and then we heat the sample up to very, very close to the melting point. So 93% of the melting temperature, 97 and 99% of the melting temperature. And we can see actually at those temperatures that the dislocations become mobile and they move around the sample. They form structures, they arrange themselves into minimum energy configurations. And the expectation was to some extent that close to the melting temperature, it shouldn't really matter how far away from the melting you are, the behavior should be roughly the same. But what we found in our experiments is that is not the case. And there's not only quantitatively, but qualitatively different behavior of these dislocations so close to the melting temperature. So that is, food for theory, of course. Here you can see the red dot is a dislocation which previously was not part of a small angle grain boundary, but it then moves around the sample. It follows the strain fields of its neighboring dislocations. In the end, they form a very nice straight line, and that is the minimum energy configuration, which is found in textbooks. And what we can here do for the first time is really follow this process in real time and in situ on a time scale of about 100 milliseconds per frame. But we hope we can do that faster in the near future. The second example is from functional materials. This is a barium titanate, which is a prototypical ferroelectric, where we can see on the left the orientation of the domains, which have slightly different orientations of the lattice planes. And that's the color insert is the angular space. So we can see islands in the angular space. It's basically a reciprocal space map. And these islands correspond to different real space locations of the domains within this grain. And then we can also do strain scans on this, and we can see the strain states within these domains. And we actually see that the decay length of the strain fields is larger than the domain size, which means that the entire domain is strained. Strain breaks the lattice symmetry, so there's a lot of exclusion rules and preservation laws which are enforced by symmetry. They do not apply in a crystal that is fully strained throughout its whole volume. And then we can, of course, do this in situ, following this domain arrangement through the hysteresis loop. So on the left side, we have the unpoled divergent state, if you want. Then you start to apply electric field. You start the formation of domains. You go to twice the coercive field. You have a very strongly dominant these pink domains. And then you start to remove the field, and the domain state is conserved, even though, well, the basic domain state is conserved, even though the domains shrink. And that is something we can do. We can loop through these domains and follow it in situ. Again, at the bottom, you have the reciprocal space maps, which have been known from macroscopic studies, and you can very nicely relate these two. Another thing which is important, especially for future users, to a technique which is quite new and not very well known in the community, is that software. And we have invested 3 years into the development of a software package we call Darfix, which is very user-friendly and which allows even non-expert users to analyze a data set and perform all the necessary steps of data selection, pre-processing, such as backtracks, noise corrections, and so on and so forth. And then the actual processing, which is specific to dark field microscopy, which is making maps of the center of mass, of the peak position, of the variance, Gaussian fitting in 1 or 2 dimensions. And we have implemented also some first machine learning algorithms like principal component analysis, independent component analysis, and non-negative matrix factorization, which will allow us to automatically identify, for example, domains in a ferroelectric without having to visually inspect these images. The article for this is under review, and I hope that it will be published very soon. So this is just an example. It's a workflow package. This means you have widgets which correspond to the different steps, and you just chain them one after another. And this is a basically complete view of almost everything that is within this package. And And the output will be publication quality images, or you can also export NumPy, Python data arrays, which then can proceed to use with your own software. Good. The timeline is that we've developed the prototype instrument since 2014 on ID6 and have operated it with users since the EBS startup until the October shutdown last year. Now everything has been dismantled and been transported to ID3, where the beamline is now under construction. I don't have any photos here, but it looks very similar to the photos that Emma showed of ID14. It's a construction site with cables all over the place and workmen running around with hard hats and shoes. We hope to start commissioning when the construction is finished in September after the summer shutdown. And we will accept then external users in full-time operation user mode in March 2024. And that means that you should submit your proposals for the September deadline this year. And I hope to see many of your proposals with many exciting projects. Thank you.
Thank you, Carsten. Any quick specific question to Carsten? No? Okay, then we move to the next presentation from Marina. See? From ID 21. No, it's not Marina. Okay. All right. So you are?
Yeah. Wow. Let's see. Yeah. So I'm not Marina.
Eduardo Villalobos.
I'm not Eduardo either.
No. Who are you then?
I'm Luis Colocho. I'm a postdoc at ID21. Marine was feeling unwell today, so she asked me to present for herself. For her.
Okay.
I have a cheat sheet.
Our best wishes to Marine.
Yes.
And also to you.
No pressure. Thanks. So, so I will be presenting our beamline, the ID21 beamline, which is a nano spectroscopy beamline in the tender X-ray domain. Yeah. So, to give you an idea of the scientific activities at the beamline ID21, I would like to start with two representative applications and to propose you a riddle. What is the common point between the sunflowers painting of Van Gogh and the movie Erin Brockovich by Julia Roberts? Maybe younger people don't know this movie, but it's about contamination of chromium in waters of the USA. And in the case of Van Gogh, it is used a chromium yellow pigment to paint the sunflowers. In both cases, researchers were interested in understanding the speciation of chromium in complex materials. And more particularly, at ID21, we welcome researchers in the field of cultural heritage and environmental science who want to determine the speciation of chromium in plant tissues like sunflowers. The scientific context is very different, but the analytical constraints are similar. In the field of cultural heritage, we are analyzing both fragments from historical paintings and model paintings, artificially aged, containing the so-called chrome yellow, which is made of lead chromate. In the field of environmental science, another group was interested in determining the effect of solutions of chromate during and after the germination of sunflower seed. Of course, lots of pieces of information can be obtained using laboratory techniques, but to get insight into the chemical mechanisms at the microscale, synchrotron techniques are particularly relevant. For the study of historical materials, samples are usually prepared as cross-sections in order to reveal the entire stratigraphy and to get the possibility to compare the composition at the surface and internally. This can give the possibility to assess the external parameters, such as light, humidity, temperature, pollutants in the degradation of materials. In the field of plant sciences, samples are also prepared in sections, usually in cryo conditions, in order to reveal the entire structure of the system. In this case, researchers focused on roots of the sunflower seeds, and they wanted to follow the effect of the metal concentration through time and the duration of the exposure, and the diffusion in the chromium and the germination of the plant. So in both cases, the experimental question is where chromium is at the microscale and under which speciation. At ID21, we usually start our experiments with acquisition of 2D XRD microfluorescence maps in order to reveal the elemental distribution of the elements of interest. In the painting, we see that chromium is concentrated in the yellow layer, while in the plants, we see that the chromium is not only in the epidermis, which is the outer layer of the plant tissue, but also it has penetrated all the way up to the xylem, which is the most internal part of the root. However, only this information is not sufficient to conclude anything about degradation or toxicity. For that, it is fundamental that we assess the chromium speciation. To answer this question, we use X-ray absorption near edge spectroscopy at the chromium K edge. Here, I focus on the painting samples. Originally, chrome yellow is made of chromate, but under artificial aging, in some conditions, chromates can reduce to chromium 3, which explains the browning of the paintings. We observed a similar structure in historical paintings, right? The next question is, how deep is such a degradation? To answer this, we exploit the fact that if we excite fluorescence map at this energy, we overexcite chromate. While if we are far above the edge, we excite all types of chromium, independently of its speciation. The signature has been exploited to produce these two energy maps, which show that in the sunflower fragments, there is indeed degradation, but which is extremely superficial, less than 1 micron. This example shows the interest of ID21 for such scientific cases, but also shows that we are at the limit of the spatial resolution. And that results are based on only 2 energies, which is pretty qualitative. And we may miss the presence of other species under this assumption. So which are the objectives of the ID21 refurbishment? Can we have a smaller beam and more stable? Can we increase the acquisition speed? Can we better preserve samples and get better combinations of spectra mapping? And in the case of environmental sciences and biology and medicine, can we increase the sensitivity? To get some objective ideas, let's put some numbers. The acquisition of these 2 maps with a submicrometric pixel size and a dwell time of 0.1 seconds took 1.5 hours. If we can decrease the dwell time by a factor of 20, 2 maps will take 4 minutes. If we manage to decrease the beam size to a square of 100 nanometers, we could get the same 2 maps for the same duration, but with much higher precision. Finally, if we keep the same pixel size for the duration, for the same duration, we could acquire 40 maps, therefore obtain many more details about the chemical composition. So in summary, we hope to get the possibility to acquire larger maps and work on larger corpi, higher resolution, work with also less dose, which is very important for biological samples, and switch from multispectral to hyperspectral imaging. In this slide, you have a technical summary of the refurbishment of ID21. The 2 main techniques are X-ray microfluorescence and X-ray absorption spectroscopy, and both of them can be combined into a spectral mapping. The beamline specifications are that we work in the tender X-ray domain between 2 to 11 keV. The beam size right now is just below 1 micron, and we hope to reach 100 nanometers. We work in vacuum, and we have the possibility to protect samples with a cryostage. And user friendliness is a very important aspect for us. As mentioned previously, thanks to the EBS and the refurbishment, we will boost our performances in terms of beam size, flux, acquisition speed, and XRF detection and cryopreservation. microscope for study larger samples, but it will be complemented and overperformed by a new nanoscope. As you can see here, the refurbishment has been taking a long time, but this year we should reach its completion. In this video, you will see the delivery of the new Nano SXM, which happened 3 weeks ago. The chamber was assembled in a clean room, which is inside the ring, and was delivered at the beamline recently. At this slide, there's a picture of the internal parts of the microscope, as well as the name of the many people involved in this project. Regarding the scientific applications, in addition to cultural heritage and to environmental sciences, we also have many experiments in the field of manufacturing materials, earth and planetary science, and health. In all these cases, the keywords for our users is the identification and location of chemical markers in complex materials. For you to evaluate if ID21 is relevant for your research, please consider this slide. In this table, we have presented in color all the elements which can be detected. And those underlined are those which can do spectroscopy, most notably 3D transition metals, phosphorus, sulfur, but also heavier metals. I hope that this presentation has been inspiring for you, and feel free to contact us for any question. 2 last slides. First, I would like to thank the 2 research groups who led the projects presented in the introduction. And finally, I would like to point out that we have 2 postdocs open, and we urgently need to hire at least 1 person. So if any of you know candidates possibly interested, please encourage them to send applications or contact us by the end of the week. As you can see on this picture, we are very happy, and we really are, to work at ID21, and we hope to see you there as user or as colleagues. Thanks.
Thank you very much. Great talk. Time for a question? Yes, we have one. Yeah.
Thank you for this nice overview. I was wondering, what about coherent diffractive imaging techniques at ID21? Is this foreseen to do some kind of spectral tycho or something like this?
That's a really nice question. So at least at the beginning of the commissioning of the new Nano SXM, it is not foreseen, but I know that they are open to it. It's just that the expertise needs to be developed, but completely open.
Thank you. So if there are no further questions, so we can go to the last presentation from the beamlines, and this is going to be given by Kirill on the chemistry program on ID24 BM23 complex. So again, X-ray absorption with a specific emphasis to chemistry.
Okay, hello. So indeed, I'm gonna talk today about chemistry, but not only about chemistry. So the talk will cover mostly the new developments at ID24 DCM beamline, the new branch that we built at the place of older energy dispersal branch of ID24. So now ID24 has two branches, energy dispersive one and the scanning one. So I'm going to talk about the scanning one. So ID24 DCM is a part of the large XAS complex of two beamlines, one of which has two branches. So first there is BM23, that is band magnet, X-band magnet, now a Wiggler beamline. Then there is ID24 energy dispersive, so original ID24 branch coupled with a high power laser facility. And the new ID24 DCM branch that starts its user operation this week. So all these three beamlines are dedicated to X-ray absorption spectroscopy for chemistry and matter under extreme conditions. The scope is pretty wide, so the focus is indeed at like matter at extremes. It's high pressure, high temperature, high magnetic fields. Then the important place is taken by environmental science and geoscience. And then indeed there is a big focus on material science and chemistry, catalysis, electrochemistry, and yeah, all sorts of chemistry. So all three beamlines do mainly XAS as a core business, but there are important differences. So BM23 is a multi-purpose, versatile XAS instrument that can do basically anything if the time resolution that is of the order of minutes per spectrum, and the flux, which is band and magnet flux, Wiggler flux, if these are compatible to your tasks. So the main focus is therefore so far it's like pretty much anything that XAS can do. And the focus is also on photon sensitive applications because we don't burn the samples very fast. So the tender samples survive. And this is often the case for catalysts, for chemical samples. So we do a lot of in situ and operandi chemistry there. So ID24 DCM that is opening these days is on the later beamline, so you have much higher flux. XAS time scale will be around 1 second for a good EXAF scan. The beam size can be focused down to sub-micron numbers, and this beamline will be mostly dedicated for studying fast processes, for studying small samples, very often under extreme conditions, to study highly diluted samples where you need a lot of photons, to study of the samples using photon 100 techniques like high energy resolution fluorescence detections, and also for multi-dimensional, multi-technique studies. ID24 energy dispersive is the beamlines that Rafaela Torquio presented last year. It's a completely different way of measuring EXAFs using a polychromator instead of monochromator in a single shot, which allows to get a very high time resolution down to hundreds of picoseconds, and it's dedicated to very specific experiments like laser shocks and pulse magnetic field and soft flow chemistry. And then the good point also that BM23, ID24, DCM, we share a lot of infrastructure and sample environments. So we are quite complementary. So a little bit more in detail about ID24 DCM. The energy range spans from 5 to 45 kiloelectron volts. So basically all relevant hard X-ray regions is covered. The beam size can be focused down to around half by half micron, but it can be also unfocused to 1 by 1 millimeter roughly if you don't need focusing, but you want to preserve your sample a little bit. X-ray flux is very high thanks to the 3 undulators that we have. Available techniques are numerous. The core business is XAS, but we can also do ESRF, XAS, X-ray diffraction, drifts, UAVs, and many more. We can measure in transmission and fluorescence and in high resolution fluorescence mode. And we have a lot of sample environments that most of it stays on the beamline, so it's of, let's say, hours. But we also can use a lot of furnaces and cell and sample environment from our dedicated sample environment lab, which is actually doing a fantastic job. I think most of you have a pleasure to experience their equipment. And then, of course, we can adapt to almost whatever equipment you bring. So if you have some setups that you designed and you want to use your sample environment, we have enough space to accommodate virtually anything. So the layout of ID24 DCM is as follows. We have, as I said, 3 undulators that help us get a high flux and cover the relevant energy range. Then we have 2 flat horizontal mirrors for harmonic rejection. Then we have the DCM, which is the heart of the beamline, which is a new instrument designed in ESRF, which is a new generation of monochromators that is really fantastic. So we like it a lot, and the commission results are very encouraging. Then optionally, we can put a KB focusing mirrors under the beam, so we can move them in and out depending on whether you need focusing or not. And finally, we have the experimental stations, the experimental setups. Apart from, let's say, generic setups where we put any sample environment, we have, let's say, 3 flagship setups that I will talk about a little bit more in detail. The first one is microXAS, microHERFT setup that couples the micro beam, so submicron beams that we can achieve by KB mirrors, with the spectrometer with 5 analyzer crystals. So we can measure, thanks to this setup, as a sample. So it's most useful for the samples where you need to do the mapping with a high spatial resolution, but you also need to discriminate between many different elements that are present in your sample. You have to discriminate their emission lines, and to be able to get the data with high spatial resolution, but also high energy resolution measuring particular elements. This is all often the case for environmental samples where there are all possible elements present. And if you measure with conventional fluorescence, the resolution of the detector is just not enough. So you have to have the analyzer spectrometer. And it's also the case for cultural heritage studies as well. So this setup is highly complementary to what is available at ID21 and ID26. The next flagship setup is designed by Angelica Rosa. So it's a laser heated diamond annual cell setup, which allows to reach a very high pressure and temperature inside a diamond annual cell. And here ID24 DCM is a very good instrument for the job, because to reach high temperature and pressure, the sample has to be very small. Because if you want to compress it, it has to be very small. And if you want to be sure that you measure in a space region where the temperature achieved by a laser heating is really homogeneous, you need a small beam. So, and also if your sample is diluted, and often it is, you need a high intensity. So you need the undulator source. So that's falls precisely into the description of ID24. That's why we think that this setup will be very powerful and highly demanded, and actually pretty much complementary to the state-of-the-art high pressure diffraction setup available at ID27. And then there's going to be still a lot of chemical studies at ID24 DCM. So this is one of the setups that we have. It's combined drifts XAS MS setup that allows to measure drifts spectra, diffuse reflectance infrared, together with XAS and together with mass spectroscopy. But it's not only that, we will also have the combined diffraction and absorption setups for chemistry, combined emission and absorption setups. So when we measure, when we do multiple techniques, we need to do measurements pretty fast. And that's when ID24 DCM will be very useful. But this is, let's say, plans to the future. In order to convince you that these plans are doable, I will show you some of the commissioning results. It's still ongoing. It will now start a smooth transition into the USM, but the commissioning is still ongoing. But first results already encouraging. So we measure XAS spectra as a core business. When you measure XAS spectra, there are several things that you need to be sure of. The first thing is the energy stability. So when you measure one spectrum, then you measure a second one, and so on. You need to be sure that they don't shift that much with respect to each other. So the energy scale has to be stable. And here is the energy stability that we achieved for 20 kilo electron volt energy, so at molybdenum edge. So we have the stability of around like several milli electron volt, 2 milli electron volt. And actually at 20 keV, this 2.39 milli electron volts correspond to the angular stability at 14 nanoradians. So 14 nanoradians is something like a human hair at 5 kilometers. So we can hit the human hair at 5 kilometers. The precision is that good. And we hope it will be, let's say, a routine operation conditions once we fix some problems with air conditioners. So it's for now it's what we have, and that's what we are pretty sure of will be, let's say, day-to-day operation. Then you need to be sure that your beam doesn't move when you measure your spectra, because if the sample is small and the beam moves a lot, then it's not good. So here for one scan at molybdenum edge, you can see that the beam position for a large beam, it's a half by half millimeter beam, so it's 500 by 500 micron, the beam movement does not exceed 1 micron. And the spikes that are seen here, they're actually not the movement of the beam, but there are, say, instabilities in the optics, yeah. So it's not a movement of the beam, but the way we measure this position. And then this is over energy, and this is over time. We measure the spectrum for 9 hours, and we see that at given energies, the beam positions does not change that much. So this positional drift is also within the order of 1 micron. And then we focus, because we'll do a lot of focused beam studies. So we will be operating quite a lot in focused mode. And these results have been achieved basically last week, by the end of last week. Using our KB mirrors, we were able to focus down to 700 nanometers in both directions. And that is the way we're going to operate this week for the first user experiment. And in the end, it's all for measuring the good data. And here I have the comparison of ID24 DCM data at molybdenum key edge with our, let's say, golden standard is BM23. So ID24 is in red and the BM23 is in blue. And you almost don't see the blue because it's line to line. So we have the excellent energy resolution, excellent data quality, and higher speed already. But with the work that is ongoing, ID24 will be even faster. So we will really reach the goal of several, let's say, seconds per exaFS, because we are already almost there. So this is not a foil, it's a real sample, it's a copper zeolite. So we measured copper KH at BM23 and ID24. And you see that the blue is, no, it's ID24, the slower scan at ID24, and the faster scan at ID24, 3 seconds per scan. Already have quite a nice data, which will still be significantly improved. And then our biggest asset is the people. We have an excellent team, which ensures the success of the projects. And by this, I thank you for your attention.
Thank you, Kirill. For this very nice and impressive talk. If I understand correctly, one thing that maybe you should emphasize is that this excellent stability that you have is not only the monochromator, but it's also the scanning of the undulator.
Yes, indeed. Here's a very big challenge, and was synchronization of the undulator and the monochromator. So indeed, all the scans that I showed and the test scans are done in a continuous scanning mode. So the monochromator moves continuously and the undulator moves continuously in order to match the energy selected by the monochromator with the gap of the undulator. This is, there's been a huge effort in this direction, and we can still improving, and things are getting better and better, but even now the results are pretty much encouraging. So we are very, very, very happy about what we see, and it will still be even better.
So a lot of progress is being done on very old problems.
Yes, yes, indeed, indeed.
So any questions, Kirin? Well, let's thank the three presentations on beamline again. Well, of course, excellent instrument and excellent beamline responsible is not all. You also have to, optimize many other resources that are more and more needed for the experimental program. Annalisa, I will tell you on the work that has been going on and the launching with the Council and SAC endorsement of a new access mode that join the usual access mode. And this is done really to optimize the experimental time from many points of view in terms of communities, in terms of changing setups at beamlines which have multitasks. To try to bring new communities at ESRF that are not necessarily expert in X-ray science. So Annalisa will drive us through the new possibilities that are now available. Thank you, Annalisa.
So can you hear me? Yes. Okay, so I'm particularly thrilled to see this very full room, because for me it's the very first user meeting in person, and it's very nice to see that many people have come here, have taken the time to come here in person to participate to this event. So what I'm going to tell you about is something on the modes of access at ESRF. And before doing that, I need to show you this slide in which there is the comparison between the applications done on each of the beamlines of the ESRF over the last 3 shifts of applications. And you can see immediately that the number is extremely high. So now, all of you are certainly aware that there is a proposal type, that there are 4 proposal types until very recently. So the standard proposals are up to 6 months, and there are 2 deadlines, and this is the standard mode. Then there is the so-called LTP, the long-term project proposal, and this is an annual deadline, and it's up to 3 years. For the structural biology, there has also been for several years something called a bug, which we'll see immediately what it means. And this is up to 2 years, and the applications are submitted once per year. And then there is also, for structural biology, the rolling proposal type, and this is up to 6 months. Now, this is very nice, and I also should say that the structural biology always looks a bit different, but it's also true that accounts for 40% of the publications of ESRF. Now, the standard proposal time request is very nice, but you must understand that we had almost 2,000 proposals submitted in 2021, and approximately less than half were accepted. In 2022, we had again almost 2,000 applications. And this means that it's more than 80 proposals per reviewer per year. And we are talking about 125 reviewers in our, what we call the BTAP, the panel that evaluates the proposals. And over the whole life of ESRF is about more than 46,000 applications. So really a lot of applications. And that really suggested that we should consider different access modes so that applications are somewhat grouped. And so instead of having one application per head, per group, we would have a group of applications for the same the same access. Now, this of course has the obvious advantage of saving time in submission, but also in evaluation of the proposals and the setting up of the instruments. And this has led to suggest a new, 2 new access models. One is called BAG, so Block Allocation Group. And this is really taken from the model that has already been successfully tested for several years at the structural biology beamlines. And then something completely new, completely different, that is called the hub proposal. Now, the difference is that both models group together the proposals and therefore reduce the number of proposals, but they are fundamentally different in that in the bug groups, in a bug, the grouping is independent principal investigators that work, for instance, on similar or different projects, but that they work independently. And of course, often, not always, but often this reflects geographical grouping. In the hub proposals, instead, the access is made on a number of PIs that work together and put together, share together the results before publication, and therefore is a way to combine resources and interest. Now, these 2 models have several advantages. First of all, they encourage the user communities to agree on important projects that can be very relevant for the community. Then, of course, ensures that there is a regular access to ESRF and uses more efficiently the bin time. Reduces also the time for changing modes between experiments, because often the experiments are grouped together, and creates an important scientific synergy within specific communities. So these are really very nice added values that these 2 modes are creating. Now, we have had some 3 pilot studies to understand how well these modes could work. And so they were 3 pilot proposals were solicited in March 2021. And so let's see very quickly how these 3 different proposals are working. So in one of the bug proposals, this was and is, because it's still running and will run up to 2026. It was science-driven and is about the structural analysis of historical materials. So this really unifies more than 10 different groups, different typically museums from all over Europe. And this bug is science-driven in that, of course, is the science that drives the functioning of this bug. And you have heard just before some of the results that have been obtained under this bug. There is another bug that is technically driven, is the shock bug, and this runs on ID 19, and is meant for the study of materials under rapid and extreme loading. So this is technically driven because, of course, it means that the users will share the same techniques, the same setup, and this is also another value because reduces the time between experiments. And then there is a hub that is currently ongoing, and you will hear more about this hub in the afternoon. And this is multi-scale, multi-techniques investigation of lithium batteries. And this has been allocated 82 shifts and is so-called the Grenoble Battery Hub. Now, this has been a pilot study, but now we are really moving to the reality. So since the 1st of January, the first round for application has been open. And so the governance of the rules for the governance, the review, and the functioning of this access have been defined. You will find them very clearly stated on the web, and they were approved by the last SAC in October 2022. And then the access modes were also endorsed by the Council in November 2022. And so at the moment, the hub proposals has one deadline on 15th of January, and we just passed one. And if I remember correctly, there were 3 hubs submitted. And this is the same deadline as the long-term project proposals. The deadlines for bugs will be on the 1st of March and the 10th of September each year. And of course, we really hope that you will use this mechanism for grouping your proposals and producing a more coherent and cohesive interaction within communities. And with this, of course, I have to thank Joanna McCarthy and the whole user office team that have developed these complex models, and they also have studied their feasibility, and they have also described the working of the governance of these proposals on the website. And with this, I thank you for your attention,